Hi everyone, Assalamu alaikum. I am Maira Farman from Electrical Engineering Department, LUMS. The paper that I'm going to review is Raman Spectra of Pyridine Adsorbed at a Silver Electrode. Before going to start, here is a short overview of my presentation. Firstly, I will talk about paper and then we'll go towards paper continuation. I will talk about modern day applications of Raman spectroscopy to highlight its importance. Then we will discuss some limitations and disadvantages of Raman spectroscopy technology. After that, I will discuss the state-of-art approaches for Raman spectroscopy. Lastly, I will conclude this presentation for Raman spectroscopy. Here we will discuss about this paper. This paper published in Science in 1974 by Martin Fleischmann, Hendra, and McEwen from the University Southampton, United Kingdom. This paper is cited by 6,698 times because of remarkable work by Fleischmann and co-workers. As Raman spectroscopy has been employed for the first time to study the role of adsorption at electrodes. In this paper, Fleischmann and co-workers observed very intense Raman scattering of pyridine adsorbed on electrochemically refined silver electrodes, which was attributed to the large surface area of the refined electrodes. The paper deals with Raman spectroscopy employed to analyze two variants of pyridine absorbed at silver electrodes. The changes in frequency and intensity of some of the bands with potential at zero charge has been taken into account, based upon which the structure of the double layer electrode has been analyzed by the author. The author in this paper, after highlighting the limitations of various methods employed in the study of species adsorption on different metal electrodes, considered studying the species adsorption on a solid metal electrode having a large surface area. The experimental setup formed by the author comprises of silver electrode. Here, silver was chosen as an electrode due to its high adsorption property. Pyridine, being a strong Raman scatterer, was taken as an adsorbate. Carry 82 spectrometer was used in this experimentation to record the Raman spectra. 100 megawatt power was used in this experiment. The electrochemical cells used for Raman experiments is illustrated in this figure. Both the incident laser beam and the radiation scattered at 90 degrees are transmitted to the optical flat glass window. The author observed different Raman spectra employing liquid pyridine and 0.05 molar solution of aqueous pyridine at the surface of silver electrode. As by authors, a strong band was examined at 1025 per centimeter, which decreased in intensity when the electrode potential was shifted to the cathode side. When the electrode was at SCE potential, which occur at 1008 per centimeter and 1036 per centimeter, the intensities of Raman spectra pass to the maximum value at about minus 0.6 volt. The paper has led to a broad analysis of the double layer structure of electrodes as well as the interaction of different species. The experiment indicates that the pyridine is separated by the electrode through a monolayer of a water molecule. In this figure, a possible model of the structure of a double layer between silver and the potassium chloride solution containing pyridine is illustrated in figure A, showing pyridine adsorbed to silver through nitrogen and in aqueous acidic environment, while in figure B, it was shown that pyridine adsorbed in aqueous environment. Here is a short video. Raman bands of pyridine in different environments. For the 1008 per centimeter band at about minus 0.1 volt, the properties of adsorbed pyridine are nearly similar to dissolved pyridine. The slight shift is indicated due to the reorientation of water molecules in contact with electrodes. The study suggests that there is more than one layer of water between the silver surface and physiosorbed pyridine. It is concluded that for more cathodic potentials, both 1008 per centimeter and 1036 per centimeter bands shift to slightly lower frequencies, while this behavior is different at higher frequencies. Here are some modern day applications of Raman spectroscopy. Raman spectroscopy has a wide variety of analytical uses. Raman spectroscopy has been exerted on the complex aqueous biological samples with no or little sample preparation because of the poor Raman scattering of water, making it an excellent analytical method for tracking biomolecules inside individual living cells. Um, as surface enhanced Raman scattering has proven to be a valuable method for variety of analysis in recent years. For gene diagnostics, self-assembled monolayer modified SERS platforms have been used. By complementary pairing, the SAM modified SERS platform can detect the breast cancer gene directly. It has recently been used in in biomedical science, single cell analysis, diagnosis, and prevention, and quantitative analyte detection in a variety of samples. SERS-based and bio-nanosensors can use the individual metal film-coated nanospheres as sensor support. There are some shortcomings in this technology. Raman spectroscopy has an undeniable drawback in that it is limited by observed fluorescence, which makes it difficult to examine the spectrum. The Raman effect is very weak. The detection needs a sensitive and highly optimized instrumentation. Sample heating through the intense laser radiation can destroy the sample or cover the Raman spectrum. Uh, Raman spectroscopy cannot be used for metals or alloys. The current state of Raman spectroscopy, including the various advanced subsets of Raman, such as the stimulated Raman scattering, coherent anti-Stokes Raman scattering, tip-enhanced Raman scattering, and surface-enhanced Raman scattering. SRS and coherent anti-Stokes Raman scattering microscopy offer exciting potential in biological imaging applications. Tip-enhanced Raman scattering are now crossing boundaries of spectral resolution. Surface-enhanced Raman scattering is showing real progress in reducing the fluorescence problem while amplifying the Raman scattering. Here's the conclusion. Today, Raman spectroscopy has been applied in various scientific fields, from chemistry and biomedical to arts and archaeology, as a powerful spectroscopic technique which allows a spectral fingerprint capable of identifying the structure and function of molecules, cells, tissues, or particle materials. In particular, its applications to medical diagnostics have been of increasing interest in the past few decades. Thank you.